Another important application of the Lorentz force is the mass spectrometer. Now remember the velocity selector. We have a charged particle that enters this region of uniform electric field and uniform magnetic field into the page. Due to the balance between the magnetic force and the electric force, QE equals QVB, we have the velocity of the charged particle that leaves this region to be equal to E over B. So plus Q leaves this velocity selector region with a velocity E over B. Or the speed is given by E over B, but the velocity is directed along perpendicular to the electric field and magnetic field. Now it enters a region with no electric field. Now what will happen? Well, we know that it's going to follow a circular trajectory inside the uniform magnetic field with the radius of the circle called r. We have mass times the centripetal acceleration m v square over r equal to the magnetic force qv cross b, but in this case we have the velocity vector and the magnetic field vector perpendicular to each other. So the magnetic field vector points into the page, the velocity vector is in the page. So it's always perpendicular to the magnetic field. And it's going to follow this circular path because the force will always point towards the center. And with that, if I isolate mass divided by charge, m over q is equal to RVB divided by v. So one of the speeds cancel here. It's going to be RB divided by v. Or we can write this as mass divided by charge, m over q is equal to, since the speed of this particle is E over b, r b square divided by E, the electric field it was subject to inside the velocity selector region. So we're going to basically obtain the mass to charge ratio as a function of applied magnetic field, electric field, and the measured radius. So by measuring the radius r, the size of deflection, and electric field and magnetic field, one can determine mass to charge ratio, m over q. So this apparatus is used to measure the masses of various isotopes of a given ion with the same charge q. So if we have a change in the mass, we can determine the isotopes within this sample by considering the mass spectrometer response. So we can measure the radius. We have a known magnetic field and electric field being applied, so we can determine the mass per charge, and therefore we can identify different types of isotopes of a given ion with the charge Q. Okay, so we talked about in the previous video, we talked about velocity selector as an application of the Lorentz force, which is QE plus QV cross B. So this is the force an object, a charged particle feels inside an electric field plus a magnetic field. And we see that the charged particles that have a speed which is the ratio of electric field to magnetic field will go undeflected through this region. And will reach a mass spectrometer which basically has a uniform magnetic field in it, no electric field, and therefore we will observe the circular path of these charged particles, and the centripetal force mv square over r will be qvb, just the magnetic part, since the electric field is zero in the Lorentz force in this region. and therefore we will have m over q equals rb over v. But we know v because it comes from a velocity selector which has a speed e over b. So those are the charged particles that go undeflected through this region of the velocity selector. So mass divided by charge is then rb square over e. When we substitute for v, e over b. So by measuring the radius, we can determine mass to charge ratio for a given magnetic field and electric field, and it is very useful in determining the different types of isotopes of a given ion.